Welcome back, everybody, to this edition of McCall Science and Enrichment Online. And today's experiment is entitled Hydrolysis of Water. What an intriguing title. Here are the materials that we will need to perform this experiment. For this experiment, you will need one 9-volt battery. If you can make sure that this is a fresh battery, you'll need a battery that is fresh and full power. You will need some thumbtacks. I have here a ball of thumbtacks that are all stuck to a magnet. Some of these thumbtacks have sort of a white paint coating on them, but the ones that I really prefer for this experiment are these thumbtacks that have just bare metal. The bare metal thumbtacks probably will work best, and you'll need at least 2 of those bare metal thumbtacks. You will need at least one clear plastic glass. You can use a tall glass, but I have these half glasses here, and these will work just fine. You will need a spoon for stirring, a good old spoon. You will need some salt. I'm told that kosher salt is preferable for this particular experiment, but I really think that any kind of salt will do just fine. And the key ingredient today is our good friend, we've used it a lot lately, distilled water. Distilled water is water that has been boiled, and then that evaporated water is then condensed and captured, and it's free of minerals and impurities. It's rather inexpensive. It costs about $1 for a gallon of this at the grocery store, and definitely distilled water is the way to go for today's experiment. So those are the materials, and now here are the first procedures. Hang on. Okay, the first step in our procedures focuses strictly on the plastic cup. So we have our plastic cup, we have 2 of our bare steel thumbtacks here, and we have our battery for measurement purposes. So the first thing we're going to do is take one of our thumbtacks and take the pointy end of that thumbtack and simply insert it through the bottom of this plastic cup here, somewhere towards the center. I have to push it a little bit, and good. So we have one thumbtack here put into the bottom of the cup. Now, the battery here has 2 what are called terminals here. We have terminal 1, terminal 2, or whichever one you want to call them, but we have 2 terminals on the top of this battery. These terminals do have a relationship as far as the electricity that this battery performs. Right now, we're just looking for the distance between these 2 terminals. So if I simply take my battery and hold it up here to the cup that has the thumbtack through, if I touch one terminal to that thumbtack, I know that my second thumbtack is going to have to go somewhere in here. Now these thumbtacks are sort of wide, and as long as the metal of the terminal on the battery touches a thumbtack in position, we should be okay. So basically anywhere in this area, I can put that second thumbtack and I think I'll be just fine. So I'm just going to line it up here and push. Oh, there we go. Okay, now notice, these 2 thumbtacks are placed in the bottom of the cup, but the metal of each thumbtack is not touching. Now when I take my battery and line that battery up, you can see that the terminals do touch each of those 2 thumbtacks, but neither terminal is touching each other and neither thumbtack is touching each other. Now you have to be careful because the pointy ends of these thumbtacks are poking through the bottom of the cup. But this is where we're going to begin our trials for today's experiment. So let's move on to trial number 1. Hang on. Alrighty, for our first trial, we start with our empty cup that has the 2 thumbtacks stuck in the bottom. We have our 9-volt battery, and we have our container of distilled water. So for this trial, I'm simply going to fill the cup with distilled water. I don't need to fill it right to the very top, but I can get pretty close. Good. Now, all I'm going to do now is very carefully, I'm going to stand the 9-volt battery up on its end so it's upright. And then I'm going to place the cup with the water and put it right over that battery. I'll move my hands here as soon as I know I'm all lined up. And I can see just by visualizing this that the 2 thumbtacks are lined up right over the terminals of the battery. The thumbtacks are touching the terminals of this battery. It's hard for you to see it because light is refracting through the water and through the plastic cup. But what I want you to notice here is what's happening here between these thumbtack points and the water that's in this plastic cup. The answer is nothing. Nothing is happening. And believe it or not, that is the correct answer for trial number 1. Now, let's move on to trial number 2. Here we go. For trial number 2, the setup is exactly the same as trial number 1. I have my cup here with distilled water. The terminals of the battery are touching the thumbtacks that are in the bottom of this cup, but right now, nothing is happening here in this distilled water. So for trial number 2, all we're going to do is add a few pinchfuls of our salt. Now the salt is still in crystal form, so we may have to use our little spoon here to stir that salt in and make sort of a salt solution here in this cup. Okay, so I put a couple pinchfuls in, and I'm going to stir that salt in so it dissolves in this distilled water. Now I'm still holding the cup so that the terminals of the battery are in direct contact with those thumbtacks. Now, is anything different? It's hard to see right now because the water is still stirring, but it looks like there are bubbles coming from one of these thumbtacks. Now, this thumbtack point has no bubbles right now, but this thumbtack point does. Those are gas bubbles coming directly from this thumbtack point. And as this thumbtack point is giving off gas bubbles, those bubbles are rising up through this distilled water, coming to the surface and popping. Now that didn't happen in trial 1, but it definitely happened in trial 2. Let's take a closer look at why this is happening. Hang on. Let's dig into some of the science behind what we just saw in trials number 1 and number 2. Now, before we begin, I need to kind of mention something here about batteries, especially the 9-volt battery. Because the 9-volt battery has these 2 terminals on top, you'll notice that one of the terminals that looks like this is labeled positive. Now, they don't say it directly on the battery, but the other terminal must be the negative terminal. So here we have the positive terminal and we have the negative terminal. And right now, this battery has what's called an open circuit. In other words, these terminals aren't touching anything to transfer the energy that's in this battery to whatever it is that's touching these terminals. So because they're not touching anything, it's called an open circuit, which means that there's no electricity flowing from one terminal through something back to the other terminal. There's no flow of electricity. So this battery, being that nothing is touching these 2 terminals, isn't really using or giving off any electricity. However, in trial number 1, when we took just plain old distilled water and we had our 2 thumbtacks here, you'll notice that, remember back in trial number 1, when I did touch the terminals to those thumbtacks, nothing happened in this water. Now, that doesn't mean that there was an open circuit. In fact, in trial number 1, we had what's called a closed circuit. In other words, when one terminal touched a thumbtack, there was electricity coming from the battery into that water, and then that electricity from the water was going back into this other thumbtack and into the other terminal. But we didn't see any bubbles. And the question is why? Well, in trial number 1, that plain distilled water by itself is not really a great substance for electricity to form a closed circuit. It's not great. But in trial number 2, we added one thing. And what was that? It was salt, sodium chloride. That salt, when it's dissolved in water, forms what's called an electrolyte. Now in trial number 2, we definitely saw this electrolyte liquid form bubbles. But here's the curious thing. Notice, I have a thumbtack on the right and I have a thumbtack on the left. Now, on my battery, I have my positive terminal and I had my negative terminal. Watch which thumbtack gives off the bubbles. So here I have positive and I have negative. So I'm going to be touching this battery to the positive terminal to this thumbtack, the negative terminal to this thumbtack, see which one actually forms bubbles. If I can make sure that this is connected, I'll be great. There we go. It is, whoop, I'm spilling salt water now, but that's okay. There. Everything is touching now. The left-hand terminal, which is the negative terminal, is giving off bubbles. And you're going to say, gee, Mr. Pete, what happens if I take my battery and turn it around? Now my negative is on the right and my positive is on the left. And I'm going to touch it the same way to that. Okay, Mr. Pete, line it up. Ah, there we go. Those bubbles are now coming from the right thumbtack. So for this trial, only the negative terminal thumbtack is producing bubbles. Isn't that strange? Now, I have one more trial that I want to show to you, and the setup is a little bit different. So hang on, here we go. All right, so those bubbles that we saw in trial number 2 is part of a scientific process called hydrolysis of water. Where are those bubbles coming from? Why are those bubbles being generated? Well, here in trial number 3, I've got some slightly different materials that might help us explain what's going on. Now, you may not have all this stuff at home, but here we go. I like this trial, and let me show you what we've got. I have a slightly taller plastic cup, and just for fun, I have added those 2 metal thumbtacks in the bottom. We may not need those, but I've added them anyhow. I've added some crystallized salt to this cup, and all I'm doing is waiting to put in some of our distilled water into that cup. So that's the same as trials number 1 and number 2. Now I still have my good old 9-volt battery. Here we go. And instead of just having the battery touching the thumbtacks here, I have some items here that are slightly different. So for trial number 3, I've taken 2 school pencils. And what I've done is I've removed the erasers from these school pencils, and I've sharpened both ends of these pencils. Now, it's pretty much the same pencil. One pencil has a slightly more yellowish paint, one pencil has a slightly more orangish paint, but for the most part, they're identical pencils. One's longer than the other, but it's not really going to make all that much difference. Now, I have poked those 2 pencils this far apart through a common piece of styrofoam just so that they stay in one place and that they're parallel to each other and they're not touching. So that's interesting, but let's put that aside for now. The other materials that we're going to need that we didn't use for trials number 1 and 2 are these 2 things. These are a red wired alligator clip and a green wired alligator clip. Now, all an alligator clip is a metal wire that has these little teethy things on the end, and if you squeeze the teethy things, they come apart, and then when you release the pressure, those teethy things go back together again. And these are used to connect the battery to something else so that power can flow and we can form what's called the closed circuit. So I've got my alligator clips, I got my battery, I've got all this good stuff. Let's just put all this stuff together right now. So here we go. So I want to put some distilled water again in this tall cup. So here is our distilled water as we pour. And just like trials number 1 and 2, I want to pour near the top, but not just over, because I'm a very messy person and I'm going to get salt water over all that, and that would be bad. Now I still have a lot of this crystallized salt at the bottom, so I do want to stir that in. Salt does help to form an electrolyte when it's dissolved in distilled water, and that's going to help us to form that closed circuit, and hopefully we'll get to see some bubbles again when we study the hydrolysis of water. So as I stir this in, that should be okay. It looks pretty good. I might have to add some more salt if we don't get the results we want, but I think that'll be just fine. Okay, good. Now, what I do want to do is I'm going to take my 2 pencils here, and I just want to put them in the water. Good, that's it. Nothing's going to really harm the pencils. You know, they can always dry out and all that stuff, but notice my 2 pencils are this far apart, and they're definitely not touching, but they're both definitely in that water, and they're still and all that good stuff. Okay, now I may have to work on something here, but that's okay. I'm going to take my red alligator clip, okay, and I'm going to place that on the positive terminal, okay? So the red is going to be on the right, and it's going to be clipped to that positive terminal. And that means that I have one terminal left, the negative terminal, and I'm going to attach my green wire to that negative terminal just like so. These alligator clips are really, really good for clipping and grabbing onto things, so this is perfect. Now, that leaves a free end here and a free end here. And you're going to say, Mr. P, what are you going to do with that? Well, I'm going to have to jiggle my camera up just a bit, and I do apologize for this, but if I raise this camera up just a bit, hopefully it won't fall over. All right. All I really want to do is show you that I'm going to take my red clip and I'm going to attach that red clip to the graphite at the center of that pencil. Now, some people are going to say that the dark or black part of the inside of the pencil is called lead. It's not really lead. It's a chemical compound called graphite. Graphite is what is contained at the center of a pencil. So the red terminal, the red positive terminal is connected to the right-hand pencil. The negative left-hand terminal is going to be connected to the left-hand pencil. Graphite, just like that. Now, it just so happens that graphite has the ability to conduct electricity. So I should have here in my container now, I should have a closed circuit. Do I see any bubbles? No, I don't see any bubbles. So what I'm going to do is this. This isn't really the way it's supposed to work. We should be seeing bubbles now because I know I've got a fresh battery and I know I've got everything connected correctly. But my guess is I probably don't have enough salt contained in this cup. So let me take a quick break here. I'm going to take everything apart. I'm going to put some more salt crystals in here, stir it up, and then we'll see if we have some hydrolysis of water bubbles happening. Hang on a second, here we go. Okay, we're still working on trial 3. I was right. I needed to add a lot more salt to the distilled water, stir it in, and create a little bit stronger electrolyte solution to allow the closed circuit to form hydrolysis bubbles. So I've got everything connected up here, and I'm going to again manually shift this camera down. Now, I'm going to have to raise this up and show you what's going on here, and I'll try to do that. I have everything connected now. There is electricity flowing from the battery through the alligator clips through both pencils. The electricity is going into the water. It's coming out of one pencil, going into the other pencil. But look, on the left hand, I have the negative terminal of that battery connected. On the right-hand pencil, I have the positive terminal of the battery connected. Now, which of these two pencils now is giving off bubbles? I hope you can see this. It's a little fuzzy. The answer is both, which was not the case in the trial 2 experiment. Now, I like this experiment, this modification, a little bit better because we can see that both pencils, which are now acting as the points of the thumbtacks in trials 1 and 2, both pencils are giving off bubbles. And the question is why? Well, the answer lies in what hydrolysis of water really is. And what hydrolysis says is this: if you add an electrolyte to distilled water and pass electricity through it, the thing that's in the water, which in this case is the graphite points of both pencils, they actually will split water. Yes, water is called H2O. That means that in one molecule of distilled water here, there are 2 hydrogen atoms and 1 oxygen atom. And when you pass electricity through it, this water is now giving off gas bubbles. So I have gas bubbles coming from the left pencil and the right pencil. Which pencil is hydrogen and which pencil is oxygen? Well, here's the thing. What do we have more atoms of in this distilled water? Do we have more hydrogen or oxygen? H2O. We have more hydrogen, okay? So we have more bubbles coming from the left pencil, which is connected to the negative terminal. That means that because we have more hydrogen atoms in this water, we have more hydrogen bubbles coming from the left pencil. On the right, We have fewer oxygen atoms in this water, so we have fewer oxygen bubbles coming from the pencil on the right. Now you're going to say, gee, how come we couldn't see any oxygen atoms coming from the thumbtack points in trial 2? And honestly, I don't know. I've looked it up, I've researched it, I can't figure it out. Maybe if you try these trials at home, you can discover which one is which. Now, it looks like I can just barely see those bubbles coming from the right-hand pencil. But here we go. So we're actually splitting water molecules into two different gases. We're generating a gas from the liquid water molecules. We have hydrogen bubbles on the left, we have oxygen bubbles on the right, and that is hydrolysis of water. So listen, everybody, I hope you get a chance to try these at home. I hope that you can do these safely without too much of a mess, and that would be a fine thing. If you have questions, we'll take your questions in class right now. We'll see you next time on McCall's Science Enrichment. Take care, everybody, and be good and be safe. See you now. Bye-bye.